Hello, everyone. Welcome to the graduate seminar of the department. This is our first session of this semester's graduate seminar. And we have the pleasure of hosting Professor Jacinta Conrad from the Department of Chemical Engineering, William Brookshire, Department of Chemical and Biomolecular Engineering at the University of Houston, here from our own university. Dr. Conrad is a physical scientist who is studying transport and dynamics within soft, complex materials and matrices. She uses a broad range of microscopy, rheology, scattering, computational methods, and similar approaches. And using those, her group seeks to understand how microscale particles, including colloids, nanoparticles, bacteria, viruses, and proteins, interact, explore, and transport through confined and crowded environments. The insights gained from fundamental studies of these non-equilibrium processes can inform the design of materials for rapid prototyping, for preventing fueling and corrosion, and for remediating environmental damage, as well as for sensitively diagnosing diseases. Dr. Conrad earned a Bachelor of Science in Mathematics from the University of Chicago. And she obtained her master and her PhD degrees in physics from Harvard University. She worked as a postdoctoral researcher in materials science and engineering at the University of Illinois Urbana-Champaign. Following that, she started as a faculty position at the University of Houston. Currently, she is the Frank M. Tiller Professor of Chemical Engineering, an executive editor at American Chemical Society, Applied Nanomaterials, and as well as the past chair of the American Physical Society Division of Soft Matter, or DSOFT. She is an elected fellow of the Society of Rheology as well as the American Physical Society. We have the honor and pleasure of her accepting our invitation for a seminar today, and we look forward to her talk. Thanks very much.
Thanks, Bert. Great. So first of all, I'll say this is a public service announcement. At noon yesterday, the first student in my class in N61 got COVID. So FYI, and I'll add, the reason I'm wearing a mask is also very practical. I was giving a talk last fall at the Society of Rheology on some of our work on transport and polymer solutions. I confidently put up my rapid test from that morning because some of our work is motivated by collaborative work I do with Richard Wilson on diagnostics, and that I don't have COVID and almost certainly had COVID and gave it to all of my friends. So for various reasons, I can talk about timing. So I'm a little paranoid and I don't want to give COVID to all of you. So if you can't hear, make some signal, but I'll do my best to project loudly through the mask. Okay. So first of all, thanks to Baruz and Kalyana for the invitation. I'm really delighted to be here to talk to you about some work looking at the behavior of mixtures of micron-sized colloids and polymers. Oops, where's my pointer? Okay, great. So why are we interested in these materials? Well, I'm going to largely focus, or I'm going to talk mostly about applications of these materials in various types of shaping processes. And so these are one of the most common feedstocks for three-dimensional printing applications. And I've highlighted a variety of materials here that can be printed, including lead zirconium titanate, various types of hydrogels, graphene oxide, and cells, all of which fall in this particulate range. But other kinds of materials are also colloidal. These can include coatings and materials that are photoactive. And so in all of these applications, there are a couple of needs. If we think about this from a very fundamental standpoint, there are two basic needs. The first is that applications require that we have some control over the phase behavior. I mix colloids and polymers together. What do they do? And in general, there's a general principle. There is equilibrium phase behavior, so that some of these mixtures can be unstable to phase separation. And if I look at a phase diagram plotted as a function of inverse temperature versus the amount of particles I put in, these systems can be metastable or phase separate, depending on where we lie in this diagram. The second feature is that polymers can also induce interactions between the colloids, and this can lead to dynamic arrest and or flocculation. And so the competition between these two different kinds of behaviors really depends on how the polymers interact with the colloids. Okay, so I'm going to talk today about two different types of interaction. The first of these is depletion. if I add non-adsorbing polymers to a mixture of large colloids, the entropy of that mixture is dominated by the entropy of the polymers, and this creates an effective interaction between those large colloids and pushes them together as the volume available to the polymers is maximized. Okay? In this case, the phase behavior of these is set by the arrest of a spinodal decomposition. So the system phase separate and the dense phase arrests. In the opposite limit, I can also have systems in which the polymers attach to the surface of the colloids. These create bridging interactions that are now enthalpic. And I can again create aggregates, but now it's because I have two large colloids that are linked by a polymer. And it turns out that the phase behavior of these systems is quite different, that the formation of solids is probably driven by a percolation-like process rather than an underlying thermodynamic instability. Okay? So trying to understand even how different types of polymer-induced interactions has significant consequences for the phase behavior. The second kind of application that I need for any form, or second kind of a characterization that I need for any kind of forming or shaping process is its flow behavior, or the rheology. And I'm going to talk today primarily about one kind of measurement in which I take a material, I put it in a rheometer, and I apply a steady unidirectional shear. Okay? And so I can turn my tool at a fixed rate and measure an apparent viscosity. And now what I measure, so that's what I'm showing here schematically. The two limiting cases are a Newtonian liquid in which the stress is proportional to the strain rate, and a Hookean solid where the stress is proportional to the strain. And typically for one of these mixtures, what I measure is something between the behavior of a Newtonian liquid, where the viscosity is independent of strain rate, or a material where I start to see strong thinning, where I start to disrupt structures that have formed due to those interactions that are present in a quiescent suspension. And so again, we can tune these behaviors by changing how particles interact. So this is perhaps a little bit too much detail, but what I want you to take away from this is that how the viscosity as a function of an applied stress or a shear rate, how that transition occurs as I vary the concentration of the polymer in solution that changes those interactions, or I vary the concentration of particles in the solution, this is for a bridging suspension, that the trends that I observe in the viscosity are very different, depending on those polymer-induced interactions. Okay, and so my group has been interested in this idea. We wanted to be able to combine some of the techniques that we use to look at both the structure of these materials using optical methods, as well as their flow behavior. I'm going to talk incompletely about some of this stuff. We came up with a model system that would allow us to do several things. So we make our own particles. These are copolymer particles. And we put small polymer brushes on the surface that both electrostatically and sterically stabilize those particles, and it prevents them from flocculating. Okay? And the nice feature of this sort of polymeric mess is that these particles can be both refractive and density matched to mixtures of glycerol and water. So we can remove effects largely of gravity, and we can look deeply into these samples using a technique that I'll explain shortly. And so what I'm going to talk about today, we have two variants on this theme. They're chemically similar, so we can create depletion attractions by adding in non-adsorbing polyacrylamide, and we can create bridging attractions by adding in adsorbing polyacrylic acid. So slight differences in the chemical functionality change the nature of those polymer-induced interactions. And so I want to tell you about two stories today. One where we're going to focus on the structure and dynamics of the bridging mixtures first. We've just started to do rheology, but I didn't include that here. And then one where we look very sensitively at how mixtures of colloids and polymers extend and break under flow. And okay, so first, why bridging? Okay. So I talked about how we can make materials, but as civil engineers or environmental engineers, bridging is very useful. This is how you flocculate particles and remove them from water. So one of the biggest applications here is in water purification, and more generally in separation. But there are also some very nice applications in making materials. So you can bridge emulsion droplets and form networks. And then really what got us excited was a phenomenon called shake gels. These are materials where you have particles and polymers that attach to the surface. You shake them abruptly and they form a solid. Okay, and that's kind of wild. So we got interested and started to think about this, and it turns out that there's relatively little understood about how the molecular weight of that added polymer that forms the bridge affects the suspension behavior and the rheology of these systems. I'm just showing snapshots from a couple of the few papers in the literature. What I want you to take away from these graphs is that the polymer and particle concentration at which these materials form solids depends on the molecular weight. A, B, and C are different molecular weights. And then the stress at which these materials yield also depends on the molecular weight. So these are from a couple of different practical scenarios, but there's very little systematic study. And so we set out to use our model system. The first thing I need to convince you is that we can actually form bridges. So we form bridges because polyacrylic acid can form hydrogen bonds that are pH sensitive with one or two of the stabilizers on our particle surface. Okay. And these hydrogen bonds are pH sensitive. So they're present at low pH and they're absent at high pH. And so we hypothesize that we should see particles that flocculate at low pH and are stable at high pH. So the first way that we test this idea is we use dynamic light scattering. We mix particles at low concentration with polymers at low and varying concentrations. We measure a decay in our spindle, and we fit an exponential to that to get out a characteristic size associated with those flocks. So at high pH, that's the diamonds that I'm showing here. What I want you to see is that the hydrodynamic diameter is independent of the amount of added polymer. That is, we add more polymer and it's largely not making big flocks. That's what we predict. We think there should not be any H bonds and everything should remain stable. If we go to lower pH, however, note that the hydrodynamic diameter starts to increase dramatically as a function of the polymer concentration. And that increase is sharper at low pH. Okay, and so this tells us that now at lower pH, we're starting to form flocks or clusters. Great. So this is an indirect measurement. I told you that we made systems that we could look at. So we use a technique called confocal microscopy, which is good at allowing us to look deeply into dense fluorescent samples because we only look at a thin plane of the sample. What I'm showing you here are movies. You should be able to see the particles moving of suspensions prepared at two different polymer concentrations. That's the top and bottom row, and then at different pH. And what I want you to see from these plots is that if I look first just at the top row, we see the formation of clusters or aggregates at low pH, consistent with our scattering data. And now, as we increase pH, we start to see smaller clusters until particles appear to be nearly dispersed at high pH. Okay. When we add more polymer, we see similar kinds of behaviors, but we see generally smaller clusters. So these are great qualitative observations, but we can make them quantitative if we use techniques that allow us to first locate the center of every particle and then either track them in 3 dimensions or track them over time in 2 dimensions to characterize different metrics for their structure and dynamics. And I'll walk through some of those. So one metric we can calculate is called a pair correlation function. This is the probability that I'll find another particle a distance r away from the center of my first particle. If I have no interactions, I expect this to increase as a step function at a normalized separation. It's equal to the particle diameter, and then be independent otherwise of the particle diameter. That's approximately what we see in the absence of added polymer. For all 3 pHs, we see something that's kind of like a weak step function. Our systems aren't perfect, but we see no, otherwise G of R is 1. So we have an equal probability to find particles at any separation. This is the behavior that we expect for a liquid. Now we add polymer, okay? At high pH, the darkest symbols, we still see an approximate step function increase. We still have a dispersed liquid, but at lower pH, we start to see the formation of a strong peak right at the interparticle separation. This tells us that we're forming networks or clusters, as we saw in those images. And we see a higher peak at the lowest pH, telling us that we're forming more local structure there. Okay? If we go to that higher concentration, we see the same qualitative trends as we saw at the lower polymer concentration, but the peak height is less at a corresponding pH. That tells us we have less aggregation. And that, again, is consistent with what we saw in our micrographs. Okay. What other kinds of structure can we measure from these systems? Well, we can look now and ask, do we have particles that are in contact with other particles? So here I show static 3-dimensional snapshots of our samples. The particles are color-coded by their contact number, the number of bonds they have with neighboring particles. And and the top row here is now a lower volume fraction. The bottom row is a higher volume fraction. And again, my pH is increasing from left to right. We see that the number of high contact numbers is greatest at lowest pH, and then least at the highest pH. Again, consistent with our mechanism for formation of structure in these systems. Okay. We can also ask about variations in longer length scale structures. We do this by measuring basically the fluctuations in the number density across different subregions of our sample, and we pick a box size for this calculation that corresponds roughly to a cluster size in the most flocculated system. Okay. So we measure fluctuations over that box size. What we find is that the fluctuations are greatest at that intermediate polymer concentration. This is again what we expect. That's where so a cluster and a void should be the same size. The largest clusters and largest voids mean the largest local structures, and those variations are smaller at a higher particle volume fraction because we just have more particles in the system. Finally, we can also look at dynamics in these systems. We can measure and track the particles over time. And we can then ask, how do the dynamics evolve as we change the pH and the polymer concentration? In the absence of added polymer, we find that all particles have diffusive dynamics on long times, independent of pH, right? They're all dispersed, and that's what we expect, okay? Once we start to add polymer, we find that upon addition of polymer, samples at lower pH have slower dynamics, and the slope of this line decreases, so that we see dynamics that are increasingly subdiffusive, meaning that we're starting to see the effects of cluster formation and caging of the particles by their neighbors. And then we get sort of weaker subdiffusion when we go to the higher polymer concentration. So what we learned from these initial studies, this is our first paper on making these systems, is that we expect to see dependence of our structure and dynamics on the concentration of polymer. But the question that I really want to focus on is now what happens when I add in equal amounts of polymer, but I change the size of the polymer. So I'm going to show that, I think, just in cartoons here. We have different molecular weights of the added polymer. I was showing you these before, the green. And what I want you to notice, we fixed the concentration of polymer in the background at half of the concentration we need for the polymer coils to begin to overlap. And what I want you to see is that both the number of aggregates that we see in the suspension, as well as their size and the number of particles in them, depends on the polymer depends on the polymer molecular weight. And there's a theoretical prediction from the early 90s that suggests, this is at least a qualitative test of that prediction. We can use the same kinds of techniques to go through and monitor changes in structure and dynamics as a function now of the polymer concentration. So here I'm going to show that G of R metric. So this was telling us about the probability of finding a particle a distance R away. And I've picked one polymer here. And what I'm going to do is increase the polymer concentration. So the left plot, I'm increasing going up. I've offset the curves. This is a better representation for clarity. And then I continue to increase the polymer concentration going down. And we put them in this order for the following reason. If I look at that first peak, which tells me about local flocculation, I see that the height of that first peak increases up to some given polymer concentration, and then it begins to decrease when I go to higher concentrations. We see this at all 4 polymer molecular weights. So this kind of non-monotonic trend is independent of the polymer size, and we see this in other metrics for the structure. So here again is that number density fluctuation metric. So how many particles that I have in a box, and then what's the fluctuations of that number? What I want you to notice again is that the number density fluctuations increase as we increase polymer concentration up to a point and then decrease. And that's true both for the lowest and the highest polymer concentrations that we look at. One thing that we find interesting, and we're still trying to understand, is that we can also ask, how much polymer do we add until the particle surface is totally covered in polymer? At that point, we would expect different behavior. Now the adsorbed polymers should act as steric stabilizers. We also determine that concentration for the different polymer sizes. And what we find is that the concentration needed to fully coat the surface of the particles is much higher than what we need to start, than the peak in these functions. Okay, so we start to see this turnover well before the surface of the particle is fully covered in the polymer. Okay, so the last point I want to make about these systems is that now thinking about how we carefully add the polymers to these suspensions allow us to tune the distribution of contact number. Okay. So what I'm showing now is a very low concentration of added polymer. Okay. This is the low molecular weight. This is the high molecular weight. This is contact number distributions, as I showed you before. What I want you to notice is there's both light and dark particles in these images, meaning I have a low contact number and high contact number. And indeed, I can separate out distinct populations. So if I look now for dynamics of these particles, some particles exhibit dynamics that look like that random walk diffusion, whereas other particles look like they're basically stuck in place. And we see that as a function at both of the molecular weights that we carefully examined, at the two in between. Okay, so why is that significant? What this tells us is that by controlling the concentration of the bridging agent, we can create mixtures that are so-called biphasic. They have both dispersed particles and flocculated particles. And this is a really interesting question for me, because this is a picture from my postdoc work. It turns out, sorry, let me rephrase that. This is a figure from a paper I wrote as a postdoc. This is really awesome data from a PhD student at U of I that unfortunately I think only appears in his thesis and in this review article. What I want you to notice is that he was looking at mixtures of particles that were flocculated and that were stable. That's labeled as phi attractive and phi repulsive. And by changing the relative fraction of flocculated and stable particles, he was able to change the scaling behavior of the elastic modulus as a function of the effective volume fraction. And so this is interesting if one is interested in printing ratios, because you can tailor the elastic modulus, so how elastic a given material is, independently from tailoring the compressive modulus. And this has implications for printability. So our current work on this project, and we've just started, I had one slide, but I took it out, I think, for time, is we've started to do rheology on these systems. And I'm going to talk about the kind of rheology that I'm really interested in doing, which we've done mostly on our other systems. So I'll talk about that next. Okay. So the second portion that I want to talk about now is thinking about rheology of those colloid polymer mixtures, the limit where we don't have any particles, where the polymers don't stick to the particle surface. Okay. So again, many material shaping processes are processes that involve flow. So I talked about 3D printing, but you could also think about electrospinning. You could think about flow batteries, which are widely investigated now for large-scale grid storage. We all care about that because ERCOT may fail again tonight. And then finally, for pathogen transmission. So if you take a picture of somebody sneezing, it's a lovely mix of particles and polymers, right? Yeah. And so and of course, how far this cloud travels depends on the flow behavior of these kinds of systems. And so for various reasons I won't talk about, we were really interested in thinking about extension and about normal stresses in these materials. Okay. So first of all, what's a normal stress? So if I think about, this is a diagram I show in the transport class that I'm teaching. Typically, if I take a material, I put it in a rheometer like the one I showed you, and I apply what's called a shear stress. So I measure the stress, I create a velocity gradient in one direction, and I look at the stress in another direction. Normal stresses mean that I look at the stress in the same direction in which I apply the gradient. Okay. And these normal stresses are, first of all, hard to measure, and second, important for a wide range of different types of processes that involve flow or dripping. So phenomena in polymers, such as rod climbing or dye swell, if you look at the soap, if you look at soap as you extrude it out of a bottle, or drop formation or migration in microchannel devices, all involve changes in the normal stress distribution. So we were interested in looking at these in a very model system. And so for the rest of my talk, I'll look at now the same particles we were using before, but now we've added in non-adsorbing polyacrylamide. I'm going to use the same terminology, so I'll pause and explain that here. We had 3 polyacrylamides to start. One is I'll call USP, that stands for uniform short polymer. Okay? So this is a relatively low molecular weight. We had something called, and a relatively narrow dispersity. We also had something called uniform large polymer, a higher molecular weight, and again, it's sort of a narrow dispersity. And narrow really means, compared to our last system, which is called dispersed polymer, or DP, where we have a slightly higher average molecular weight, but a whoppingly large dispersity. Okay, very broad distribution of sizes. And we took these systems and we put them in our shear rheometer, and we did the tests that I told you about earlier. We made a unidirectional measurement. We increased the stress where we flowed the tool, and then we measured 2 quantities, the viscosity and then the first normal stress difference. Okay. So what did we find? In the case of the uniform short polymer, we find that in the absence of added polymer, the particles behave roughly as a Newtonian fluid. That is, the viscosity is independent of the stress. Once we add polymer, we see two things. One is that we see what's called shear thinning at low stresses. That is the viscosity decrease as we increase in stress. We see a modest increase at higher stresses. And this is the behavior called shear thickening. We measured at the same time what's called the first normal stress difference. What we find for these systems is that the first normal stress difference is effectively independent of stress. It's weakly dependent. It gets slightly negative. You can see that by comparing where these points are compared to that line, which is 0. And it decreases slightly at high stresses. Okay, great. So we understand how these materials flow. If we add in polymers now that contain long polymers, either our uniform large polymer or our dispersed polymer mixtures, we see one very different behavior. First, we still see the thinning at low stresses. We see more pronounced thickening at higher stress. But what's really different is the behavior of this first normal stress difference at high stress. Now it shoots up to be strongly positive in both cases as we add more and more polymer. Okay. And the reason that I think this is really interesting is that if I go back and I look at these samples using our confocal microscope, they basically all look the same. Okay. So that the quiescent structure, there's something very different happening in the flow behavior of these systems that's not captured by that quiescent microstructure. Okay, cool. So how do we understand this? The first comment is that there are two models for why materials can thicken, right? So if I apply a stress, why does it get thicker? The first of these models is due to Norm Wagner and John Brady, and this is a model called hydroclusters. What they proposed is that as you shear particles, you force them into contact, but to get them to contact, you have to push out the fluid layer that's between them. Okay? This forms what are known as hydroclusters, and the increase in the overall viscosity comes from the fact that it's hard to displace that very thin fluid layer, and it gets harder and harder as that fluid layer gets smaller. More recently, Jeff Morris, Martin, and collaborators proposed a second mechanism based on observations of sand. So if you go to the beach and if you go down to Galveston and you step on the sand in the wet part, okay, and you look at your footprint immediately after you take it out, you'll see that the footprint looks different than the rest of the sand. This is a phenomenon which is also common to other kinds of environmental porous media called dilation. Okay, that is that the sand pushes back on you. And so they proposed that, and this is due to the formation of a frictional network now of particles. So the second mechanism that was proposed was that these frictional networks could form instead, where particles are coming into close contact, and the particles pushing back against each other is what increases the viscosity. Okay. So I'm going to light over a fair bit of detail because it's not really what I want to talk about. But we went through and using a model in the literature, we were able to identify what appears to be a diagnostic for what causes thickening. Sorry, and we're following others. We applied this model. I don't want to take too much credit. Okay. The key point of the model is that it was proposed that the sign of that first normal stress difference is related to the fraction of particles that are in frictional contact. And so what we find, we fit this model, what we extract out is this fraction of particles in frictional contact. There are more details if you care, I can tell you later. But what we find is that if we look at systems where the first normal stress difference remains negative, even at high stress, that we get a low fraction of particles in frictional contact. If we look at systems where we have a first normal stress is positive at high stress, we have a high fraction of particles in frictional contact. And so what we proposed from this idea, I think that's too much. Okay, that's too much detail for right now. Okay, so what we proposed for this idea was that what was driving the difference then, even though we have nominally the same background rheology in our polymers, is that the size of the polymer matters. Okay, if we extend fully the polymer, which we know they're extended, given we know they're extended, okay, and we compare then the size of an extended polymer for the short and long polymers to the average separation between the particles in our suspension, we find that the extended small polymers will fit largely in those gaps, but the extended large polymers were not. And so what we think is happening in this system is that as we shear the system, large polymers get pushed into larger voids. This allows particles to come into contact to form those frictional networks. But small polymers are not excluded by size, and so they continue to lubricate them. So we think we can tune now the thickening mechanism by changing the size of the polymers. Okay, that was all a long introduction to what I really want to talk about. So this mechanism really depends on the fact that these polymers are extended under the conditions that we flow them. So I naively said, without really knowing very much, let's think about extensional rheology, right? Instead of looking at shear, I want to look at now taking a filament and stretching it out. Okay, so this now has obvious connections to printing processes. The three-dimensional printing process. This is a picture from my postdoc advisors group. Okay, here they extrude suspensions through a small nozzle and draw it out. Okay, that's clearly an extensional process. And now there's a body of literature looking at extensional processes in particle solutions, and you can get all sorts of wacky behaviors. You can get small nets that form as you can get large nets that form, and you can even get these suspensions to fracture. Okay? And all of this in hard particle suspensions depends on the particle volume fraction. So of course, we were interested in trying to look at now not just particle systems, but mixtures of these non-adsorbing polymers and the particles. So to do that, we use a relatively new technique called dripping on substrate rheology. This is a cheap and dirty way to do extensional rheology for suspensions that aren't too stiff. Okay? And the system is almost as simple as I've described. We take a needle, we put a droplet on a surface, the droplet partially wets the surface and spreads, and this then creates a thin, slender filament in the net that over time becomes thinner and thinner as capillary forces drag the droplet out. And we measure the evolution of that net radius as a function of time. Okay, so there we go. Very simple measurement invented by Vivek Sharma at the UIC, but really powerful for what I'm about to tell you about. Okay, so this is great, by the way. This is using a goniometer already in the lab and a syringe pump already in the lab, so we got to do this for free. Okay, so the first thing that we started out by doing, we want to look at colloids and polymers, but we weren't there yet. So we started out by just looking at the solutions of the background polymers, because it turns out that nobody had ever done this, in the sense that nobody had said, let me make a series of polymer solutions, same polymer, same solvents, but vary the polymer molecular weight. So that's what we did. We now have, I've changed different students, so different color on these diagrams, but the same three polymers: uniform small, uniform large, and disperse. We make a series of solutions at different concentrations relative to the overlap concentration. And we look at now the thinning behavior of that net as a function of time. What I want you to take away from the static snapshots from each of these movies is that the time scales on each of these are different, both as a function of the polymer size and as a function of the polymer concentration. Okay? So these dynamics depend both on polymer concentration and polymer size. Okay. Of course, we can make this quantitative, and we do that by using image processing algorithms to extract out the net thickness as a function of time. What I'm doing now is showing that data for 4 different suspensions. One is just the fluid. That's what NP really means, fluid, no polymers. And then for 3 different polymer solutions at the same normalized concentration. And what I want you to notice from this, I'm going to focus on these dashed lines. At long times, what we find is that the solutions that contain polymer exhibit an exponential dependence. That's the dashed line fits. This is called the elastocapillary regime, where a competition between elastic and capillary forces leads to filament thinning. There's a model for the expected behavior. Note that it includes an exponential dependence, and from that exponential dependence, we can pull out a characteristic relaxation time, which is lambda sub e. Okay. Although this fails at the very end, and you can see that in these 2 curves here for the disperse and the long polymer solutions, you can see that our experimental data, the symbols, fall off that line. That's because after we pull out the polymers so far, we can't extend them any further. And so the fact that they're only extensible so far up to their length leads to a different scaling behavior on long times, and that's that last little bit. Okay, but I'm going to talk mostly about this. So we can characterize an average extensional relaxation time. This is lambda sub e. Okay, so we make a whole bunch of measurements, and I'm going to throw all the data up, and then I'm going to tell you slowly how to understand it. I'm plotting here the extensional relaxation time as a function of a normalized polymer concentration for the different molecular weights. What I want you to take away from this are 2 things. One is that there's this intermediate regime where all of the data have different slopes, and the slope is given by that number. They all scale as a power law with the extensional relaxation time scales as a power law with concentration. But the power law depends on the polymer size and dispersity. On long times, polymer dynamics predict that the scaling should turn over to 1. We see that on 2 of the, at high concentrations, not long times. We expect that we see a scaling of 1. We see that for our long polymer solutions. We just can't get high enough in concentration for the short polymer. Okay, these are numbers without context. Why are they different? So at this point, we talked to my friend and collaborator, Vivek Sharma at UIC, who is very interested in thinking about extensional behavior of polymer solutions. And he had done two things that were very clever. So first of all, he developed a model that suggested the fact that we should be able to predict the scaling behavior of the extensional relaxation time simply from properties of the macromolecules, okay? And specifically from the parameter nu, which is the excluded volume parameter for polymers. And in his picture, okay, a new value of 0.58, which 0.588, which corresponds to a good solvent of the for the polymer, would lead to a scaling exponent of 0.31. And the physical interpretation of this is that excluded volume interactions are important. Whereas the value of nu equals 1/2, this is called a theta solvent. This says the polymer and solvent like each other equally. This says the polymer likes the solvent more, would lead to a scaling exponent of 1. And so that all of the excluded volume interactions are screened due to chain stretching. So then he did something very nice. He took two polymers where they had the same overlap concentration. One was more flexible and one was less flexible. They're labeled here, and measured those scaling exponents. And he found that for the less flexible one, that indeed he measured a value of that exponent that was very close to what he expected. But the more flexible one had an exponent that was somewhat less than 1. Okay, so how did he explain this? Okay. So a second behavior that occurs for stretched polymers is what's called coil stretch hysteresis. That is, if you take a polymer and stretch it out and then let it go, it comes back to it under certain conditions. It can come back to itself under a different pathway. So this has been demonstrated nicely about 20 years ago using DNA. You can see that originally it's coiled. They used optical tracers to stretch it out. And then when it collapsed, you can see that it was less extended later. Right? Okay, so coil stretch hysteresis could be one reason why just the macromolecular parameters of the polymers alone aren't enough to explain their flow behavior. Okay, so what determines coil stretch hysteresis? Well, this is really asking what's the hydrodynamic drag on the polymer when it's stretched out and when it's coiled up. Okay, so there's a nice model from Ron Larson's group at Michigan that says that the coil stretch hysteresis can be predicted from the ratio of the drag coefficient of a stretched polymer to that of a coiled polymer. And now, if you go back and you calculate that, it can be related back then to several things: the contour length of the polymer, the unstretched size, and then the segment of what's the diameter of a cone segment. And so the Larson prediction is that coil stretch hysteresis should occur when this ratio is greater than 4.5. So Vivek went back and tested this on his data and found that his data was consistent with this idea. When the ratio is low, he measured the m equals 0.32, telling that excluded volume interactions were not screened. Whereas at a value that was somewhat higher than this threshold, coil stretch hysteresis led to partial screening of those excluded volume interactions. Okay, so armed with this theoretical framework, we can now go back and explain our polymer results. I'll walk through them one by one. So first, if we look at the uniform small polymer, okay, if we calculate the ratio of those coefficients, it's 0.32. The scaling exponent that we measure is close to the good solvent limit, where we expect excluded volume interactions to be dominant. And that's what we see. Now, when we go to the uniform large polymer, we measure a value that's just above that threshold. We measure a scaling exponent that's in between. And so this suggests two things. One is that the excluded volume interactions are partially screened, and that likely we have an onset of this coil stretch hysteresis, which is responsible for that deviation. And then finally, when we go to the dispersed polymer system, and I should just remind you, the dispersed polymer has the highest average molecular weight, but also is very broadly distributed in size. We see two things, right? First of all, if we use the average sizes and we calculate that ratio, we get a value of 6. We see a higher scaling exponent, again, consistent with a greater onset of coil stretch hysteresis. But what's also very interesting is that this model predicts that we should transition back to the scaling of 1 set by the Rouse dynamics of the polymers at C over C star at right when the polymers begin to overlap. But if you look at our data, it's better modeled by the dashed line, okay, which is at somewhat lower concentration. And it turns out what this suggests is that if we use a different average, so for polymers, I could weight every molecular weight by the number of polymers with that molecular weight. I could weight every polymer by its molecular weight. And it turns out that the weight average molecular weight does a better job of predicting where this turnover occurs. Okay, that's a lot of words. So what we learned from this is that we can now say we can predict the flow behavior of our polymer solutions simply from the polymers, and we can tune how these systems extend and coil through their molecular weight and molecular weight distribution, which is cool. And so in the final bit of my talk, I want to now take these ideas and apply them to what I really want to look at, which are mixtures of colloids and polymers, which gets harder. Okay. And so there's some mathematical reasons why this is harder. Okay. But it turns out that there are some reasons why you might expect adding polymers will make things more stretchy. Sorry, particles to polymer solutions would make it more stretchy, and other reasons why you would expect it to make it less stretchy. Okay. So the first thing that we do is we compare the responses in extension for our solvent, which is this glycerol water mixture, for the polymer solutions, and just for a suspension of particles without any added polymer. And again, I show snapshots from those experiments up top. Okay. So first, if I look at the polymers, if I look at the evolution of the filament, okay, the solvent exhibits a viscous response. The polymer solutions exhibit a transition from what's called a power law scaling to that exponential scaling. And then if we go to long polymers, we can't extend it any further, and we get to that terminal viscoelastic-capillary regime. The viscous particles, the dense suspension, though, exhibits three regimes that all scale linearly, where the radius evolution scales linearly with time. And so this is what's called a viscocapillary regime, where the extension is set by the viscosity and the capillary effect. Okay. And so this is in some sense very similar to how granular extensional flows, but there's some subtle differences we're still trying to understand. Okay. We can also take these measurements and extract out an extensional viscosity. So what is our resistance to flow under extension? And again, marching through our data, if I start with a solvent, it's approximately constant. And you can see, where do we start to have resolution limits? That's what the error bars are. Okay. The polymer solutions go down, up, down, and then up. Okay. And that's because we change scaling regimes. So we get different dependence of that. We see different dependence of the extensional viscosity. And then finally, the dense suspension is nearly constant. And that's because the scales linearly with time. Okay, so now how we can go back and do the same measurements on solutions that contain both particles and polymers. Here are all the data. Okay, it's all color-coded. We're going to again focus largely on this last regime. That's the dashed line fits. And so let me talk you through what we see. Okay, so the first thing I say, I'll show you data, and then I'll tell you what you need to take away from that. So that's our data. It's color-coded. Okay, we can take the data and then calculate the extensional viscosity as a function of the Henke strain, or local strain measure. I should have pointed out here, what we see is that the filament breakup, as we increase the concentration of polymer, we see that the radius evolves more slowly. That's what we see is that as we increase the concentration of polymer, the suspensions have a higher extensional viscosity. Okay, but what I really like about the measurements that we've done is that we can now ask a question. When I add particles or polymers, what is controlling how these suspensions both extend and break up? Okay, so the first thing I'm going to do now is compare. We have all the data. I'm just going to show a couple of it. I'm plotting the extensional relaxation time as a function of polymer concentration for two sets of samples. The original polymer data, this is shown in both cases as the open symbols, and then our suspensions that contain particles and polymers, that's the closed symbols. What I want you to take away from this is that everything collapses onto a single curve. This tells us that extension is dominated entirely by the extensional behavior of the polymers. The particles are along for the ride. They don't care. Okay. That's actually very interesting. This gives us one way to try to think about the extensional behavior. And it doesn't matter on the particle size, right? It just follows exactly the polymer curve. Sorry, the polymer size doesn't matter. The corresponding mixtures follow exactly the polymer curves. Great. The other parameter that we've looked at carefully, and I'll have to explain this, is the time that it takes that filament to break up. So all the way at the end of that radius evolution curve. Okay? This is really practically relevant. This is nice. And sometimes this is model independent. It doesn't matter what regime of filament thinning we're looking at. It just says, how long does it take to break up? And so you could imagine if you were creating an electrospun material, for example, that you care about when that's going to break, or if you're trying to create materials through droplet formation. What we find, this is a little complicated, I'm not showing the first data, is that we can create a scaling plot where everything approximately collapses if we plot not the filament lifespan, but a normalized quantity. So we take the filament lifespan, for example, for our polymer solutions, that's the open symbols, and we divide that by the filament lifespan of the solvent. We do the same comparison for the particle solutions, except now we take the lifespan of the suspension. So we're looking at TF naught here is the filament lifespan of a corresponding mixture in the absence of polymer. So in the absence of particles, that's just the solvent. For suspensions that contain colloids and polymers, that's just the colloids. Okay. Note that everything again collapses approximately onto a single plot. And that says that adding polymers, whether it's to solvent or to a colloidal suspension, has the same effect. And so again, what we like about this is that I've shown you two results, and I should probably highlight this a little bit more. I showed you that we tune the shear rheology, which is dictated by the colloids, okay, and whether or not they come into contact. That depends on the polymer size. But the extensional rheology is really controlled by the polymers. And so this gives us ways of now thinking about how to process and shape these materials. Okay, so I talk fast, so let me tell you just the take-home messages. We've developed a really nice system where we can controllably stick particles to polymer surfaces, and we can tune how strongly they stick through the pH. And we show that we can make a variety of different phases that depend on the molecular weight of the added polymers as well as the concentration. And we think this will have interesting consequences for rheology, which is what we're starting to do now. Okay. I've also shown you in mixtures of colloids and non-sticky polymers that the molecular weight affects how suspensions thicken when we have shear, but really the thickening is dependent on the colloids. It controls the elastic response entirely when we extend it rather than shear. And then we can think about now how we tune the printability of these materials through molecular weight distribution by controlling those breakup times. Okay, that's what I wanted to tell you. I want to make sure that I acknowledge both the people who pay us to do things as well as the students who do the work. Our bridging work is led and done mostly by Mariah Gallegos with some help from Diego Sotrisno. Our shear work was in the depletion mixtures was started by a former student in Park, who now works for, I didn't fix that, a company called Daisy Brand. I always want to call it Dairy Brand, but it's not. They work on dairy, that's why I can't keep it straight. And our extensional work is done by Diego Sotrisno. I'd like to acknowledge some really great collaborators. These are a lot of folks. The people who contribute here are shown in red and green. Of course, I need to thank all the people who helped to pay for things. You for your attention. I'd be happy to take questions now. Thank you.
Thank you very much, Jessica. We have time for a couple of questions and discussions.
Yeah.
Hi, Susan.
Hi, Susan.
I was curious, in your bridging series, is the absorption for your samples, is that reversible or?
So I have to admit, we haven't really tested that carefully. The question, I'll speak loudly for the folks online, is in the bridging mixtures, is the absorption reversible? I suspect not, because I don't think H bonds are going to be very reversible. We've never really tried to reverse it. We just say that the mixtures are what they are. We need to do that. Okay? We at least try it. We really haven't in a way that I would feel comfortable saying anything. But I think it's going to be strong enough. The one thing I'll note, it's tunable by pH. So we should, I don't know what a hydrogen bond does. This is maybe my ignorance as a chemist or not. What a hydrogen bond does when you turn it off. But we'll go look at. We need to go look at that. But I don't know. It's a good question, right? Because that would be even more haven't done it.
I'm curious, like, if it's not, maybe matter.
So the mix, that's a great question. The mixing matters. We know that. So when we've worked out for all of these systems, we actually have fairly detailed protocols for how you make them reproducibly. One thing that's complicated is shear measurements. So, and I'll be very careful about that, is that at a fixed that you can, once you start to attach particles to the surface of the particles, once you attach polymers to the surface of the particles and you shear it, you break that bridge. And so, and that bridge doesn't reform as quickly once you have it now in a rheometer. And we know that we can show data. There's also really nice data from folks like John Berg at Washington who've looked carefully at this process of absorption. And so I don't shearing alone. And so the other thing I'll note is I showed a picture of a bridged emulsion system from Pat Doyle at MIT. There are other folks looking at these systems. One of my former students, who's now at Rhode Island, also Ryan Pulling-Skutbeck, also Matt Helgeson at UCSB. They've also looked at whether now emulsion droplets bridged by polymers are reversible. The answer is no. Even there, where the interaction's a lot easier, that they don't reform the same way. And so they might fall apart if we change the pH, but shearing does different things because they are history dependent. You can make them reproducibly, but you have to be careful with their shear history. Does that answer your question? Yeah.
On the students. I don't this is whether they my question is regarding I put articles. If I heard correctly, you said that the concentration of constants do not have any effect on the extension of growth. Can you give a simple explanation why is it true only the concentrations you considered, or
I'll be very careful about that. So Kalyan's question is, why don't the particles contribute to the extensional response? Is it only a function of the state points that we're looking at, or is it more generically true? So let me give at least a couple answers to this. So I did my PhD a long time ago on partly on colloidal gels. And so in colloidal gels, and as a physicist 20 years ago, the polymers we would add were an effective field of interaction, okay? And so from that perspective, I was shocked that I promise I'm answering the question, it's gonna be in a roundabout way. I was shocked, right, that the particles didn't seem to contribute to the extensional response. When I take this result, and I was at a meeting last week, and a meeting 3 weeks before that, and I show it to folks who, for example, are rheologists, whose primary home of comfort is thinking about how materials flow. They said, of course, in extension, you're pulling the particles off. There's nothing, they're not. And so I said, well, are they going to bump into each other? Well, so my friend actually said, well, they're going to bump into each other. You're actually, when you deform them, if I take two particles, they're not going to encounter each other if I'm pulling them apart this way. I said, well, it's getting thinner this way. If the filament's thinning, shouldn't they bump? I said, shouldn't the normal stresses matter? That was my original motivation. And it turns out that's a really complicated question. And it's one that has become, so I was talking to folks again this week, and that's a really hard question. So it's still stunning to me. There's no general relationship between normal stresses and extensional flow, which I feel like there should be. And we talked to somebody who would know the answer to that question if it existed. And so, and the reason is that, and try not to be too technical, is that how materials deform depends on what they are. And so the colloids don't bump into each other. The polymers can stretch out. They are really different systems under extension. And so now let me add one more thing. The reason why we're interested, so as a naive physicist, when I say that, all colloidal gels to me at once upon a time were the same. It didn't matter how I induced those interactions, right? It's an effective field. A lot of what I've done as a faculty member is be like, oh no, the polymers are not an effective field. They really matter. Their size distribution matters, their size matters. But there are other ways to create polymer-induced interactions, or even just interactions at all. So now if I took, for example, a colloidal gel suspension that didn't have any polymers in it, that had contact interactions, I feel like the particles would have to dominate that response, but it may not look very different than a system that's dense. Does that make sense? But nobody has done that experiment to my knowledge. It's one of the ones we're talking about doing. And so that was a long answer. So I think here, because we're at a high solids loading, but not super high, the particles don't matter, because what's really controlling the extensional response is the fact that the polymers can extend. We're pushing up to higher particle loadings. Our data so far are not conclusive, so I don't really want to say very much. I think we'll start to see some effects once we just get too many particles in there, because I showed you pictures of fracturing suspensions, right? But we haven't gotten there yet. But we're still at a pretty high solids loading. We're high enough that at least in shear particles bump into each other. So I was really surprised. I think it will probably have some parametric dependence. It will also depend very sensitively on the nature of those interactions. That helps. Does that give you a physical picture?
Yeah, one more question.
Yeah, sorry, I give long answers, and that's why I summarize.
some of them are pressing issues, we may not even have answers. So if we have a plot where on the x-axis you have R over 2A.
Mhm.
And we got like years.
Yeah. Oh.
That beats R over 2A is equal to 1. So again, I don't know rheology and I don't know.
That's why I was trying to be very careful. So this is a pair correlation function. It's actually, let me go to the other one. This is the prettier one, but I'll go to the one that has the cartoon on it. which I threw.
When G of R is fine, I'll take it up.
Yeah, well, it's the same thing, right? So what this is showing you, this is asking very simply, how do I expect to see a particle some distance R away? So if I have a uniform, oh, sorry, do you want to, is that your question or?
Yes, especially in statistical mechanics,
Mhm.
you have this critical phenomenon, a lot of parameters. So whenever you have these kinds of peaks, you have one behavior, low numbers, another behavior, number, and you have speed. There is some critical phenomenon or.
So this isn't the way that you would look for critical phenomena in these systems, but you.
Is there a critical phenomenon in the system?
So in dilute colloidal gels, there are critical phenomena that you can map directly back. These are what are called concentrated gels, and there's not a critical. So, and what's really, so in the dilute limit, what sets gelation is the fact that you need to form a spanning network in your short particles. And so it ends up being a percolation-like condition, which then has a critical exponent, right? In a concentrated limit, there are two things that come in, right? One is that will actually make me change that. So that's when I have particles that stick irreversibly and don't break. When I have either lots of particles or bonds that can irreversibly break and form that shift. But these don't, I don't think these have critical behavior, in part because their interactions are sorry, the bridging systems don't, because you can see that I have coexisting populations of both flocculated and non-flocculated systems. So these are not going to have critical ones, critical behavior. But for dilute gels, you can plot them as a function of a normalized variable and see a sharp divergence. So here, what we're just simply measuring is the evolution of structure. It doesn't appear to have a critical onset for the reasons I just described. But yes, there are some really nice studies from about 30 years ago in this space. I.e. what I was reading when I was a PhD student.
Let's just not see it. I guess I have a question. So you showed the plot, you showed that you share viscosity condition, viscosity shear. I was curious, you also measure relation of shear stress and friction relation with shear limits. Consistent shear. Mentioned how the vary with additional polymers.
Okay. So let me go back to those plots. So we haven't measured, so the question is, do we measure frictional coefficients and what else?
And shear strength of materials.
Yeah, so we haven't with these because we weren't interested in it. We can do rheology experiments that allow us to measure viscous and elastic moduli to look at shear stress and storage. We haven't for these systems because I was obsessed with normal stress differences, to be honest. And I was really looking I wanted to do those measurements. And so we got very good at, but we had some other reasons for why we did there. You can. I'm trying to remember. So for folks who look, so these systems will behave, this system will behave like an elastic solid on some frequencies, right? They form networks that are load bearing. They're rather weak at these given concentrations. So they're going to break up very easily. So their relaxation time is fairly short, but we can measure elastic moduli in these. I have some data somewhere, but I don't know where it is. We haven't published it. But mostly for this system, and especially now that we're really focusing, well, because we're so interested in the extensional, what the critical physics of the extension is controlled by the unidirectional deformation. So I've always, and so my student who's looking at bridging is doing some measurements of the elastic and viscous moduli here, but we have not studied this perfectly. But you can, we just have it. I don't know how to measure frictional coefficients. Maybe we should talk about that afterwards. Yeah, I don't know how to measure that. So if you could tell me, because again, that would be well.
You are measuring shear stress and normal stress. But if you find any third measure on the same plane, essentially by dividing those, you will have the friction analysis.
You know what I just realized, I don't know if we've ever done. I don't know if you've ever done. So in like a linear measurement.
It depends on, it doesn't have to be a linear.
Okay, well, we could potentially pull it out of these, because we also have, well, I lied, we applied, I don't know what we captured. So we applied, this is a stress controlled rheometer, so we apply a stress and we measure a viscosity. So I don't know, we're not measuring a stress, right? Apply. We have a torque.
But is your essentially measuring the sensor?
Right, we apply a stress, we measure a torque, right? And so, yeah, I need to understand how we would actually do that, because this is an applied stress measurement.
So we'll have to talk more about this. I have a related question.
Mhm.
So you show measurement of shear terrain and flow, but I was not shear or strain rate. I was wondering what is the range of this terrain there? That's a
Do you remember where that is?
polymer size.
Here?
Large terrain or small terrain.
Hold on, I think I know what you're talking about. Let me just confirm this. Yeah, this is a heavy strain, so. It's a strain, so it's dimensionless. So this is related to the extension of the polymer. These are large strains, right? We are straining a polymer fully as we break it, right? We see, we're getting to fairly large strains in the extensional measurements. This is, I mean, so right now, because, sorry. Oh, I should note, and tell me, I'll thoughts too, that the strain, what's driving our straining process here is really this capillary thinning. And so we have a poor ability to access higher strains than this, right? Because we're basically just watching our filament drain and spread. One of the things that we're doing that I just paid a lot of money today is getting Ramadan Krishnamurthy's extension or rheometer working again, so that we can actually do proper filament stretching. And then I think we should be able to go to higher strength, but
these are
these are already pretty large. No, these are large, right? Yeah, one of the things we're interested in is varying strain rate, especially for the bridging suspensions. We've started these measurements, they're just too stiff, and also going to the higher volume fractions is very stiff. So being able to apply a sharper displacement will be useful. So we're getting that fixed, so we can do that better. Great.
Back to this here.
You said some functional models.
Oh yeah, no,
What was the connection?
right. So let me be. I'll sort of care. Okay. Let me. This is the hidden slide. Is it big enough? Let me tell you what I actually mean here. Okay. So there's sort of two pieces to this. Actually, let me unhide it so I can display it so you can actually see it. So what it is, it's a way to model thickening based on the fact that instead of thinking of a thickening material as a uniform material, you think about it as two materials that each have critical divergences at different viscosities. And so the model is shown in its mathematical formulas. And here you have one fraction of your material in one fraction of the material in the other. Here, this is the fraction of particles in frictional contact, which is related to which decays exponentially as a function of a contact stress that should be predictable. So there's a lot I haven't shown you. So that's the model, but the basic idea is that you have two different types of divergences here. And so the diagnostic for that, I didn't show either. This is work now looking just at particles. This is to convince you that it works. These are small silicon nanoparticles. And what, let's see, Blair, Hudson, and collaborators did. And what this is really nice, they changed the fraction of, and so actually, I don't remember. I have a slide somewhere on the theory in more detail, and I don't think it's in here. But I can tell you more. I can show it. Well, that's one of the divergences, right? One of the divergences jamming. Yeah. So, and there are two separate divergences. One of them is controlled by contacts. One of them is controlled by. And so here, what these folks showed is that the sign of the first normal stress difference, okay, is correlated to the thickening behavior. And if they go through and they apply, they turn the crank and they back out the fraction of particles in frictional contact, they get this nice correspondence between the thickening of the sign of that first normal stress difference, and then from fitting the curves to the model, the fraction of particles in frictional contact. let me check one more hidden slide. I don't remember if it's hiding in here. No. Ah, there we go. Yeah, so here, let me unhide this too. So this is more, that's what I should have found. I forgot that was there. Okay. So this is the model. Okay. And note that you have this, it basically says you have both types of divergences that I talked about, both the lubricated ones and the frictional ones. They diverge at different volume fractions because particles that are rough can touch faster than particles that are smooth. And the fact that they diverge at different volume fractions means that you jam at some volume fraction between them. So that's the physics of that model. Does that help? Yeah, sorry. And in a longer talk, I would, or one that I didn't want to stuff so much in, I would talk a little bit more about that. Right? That's the idea. And so I should note that, yeah. And so this is of course really interesting for folks doing construction, right? Because you have materials that are ultimately going to jam and thicken.
An example
So the question I think is, have we looked at anything besides colloids or are beautifully tuned? No, because we beautifully tune them to do many things, which is fine. No, when I was at this polymers conference 2 weeks ago, they were like, "It'd be very dissolvent," and I said, "No, we tune it to do a variety of beautiful things that you're not appreciating." So no, I mean, I think so. So I'll note there's not much work on extension of particle laden suspensions, and there's one of two. Maybe very careful. In terms of particle polymer suspensions, there are 4 papers. 3 of those are granular, and 1 is at lower particle concentration. So, and it's in a table in the manuscript we're about to resubmit, right? That's why I can count 4. And so clays, I don't think people have looked at them, right? They're a lovely system. They're not as, like I said, we wanted to tune many things, so this is beautifully chemistry controlled. These are perfect, right? But of course, if we can get techniques working, we can apply them to other systems. And so this is like I said, this technique is nice if you have suspensions that are not too stiff. We're paying to renovate Ramanon's rheometer to do stiffer. Clays might be stiffer because you have very strong contact interactions depending on the charge interactions, right? Fair enough, right? Yeah, and I've never worked with clay particles, but of course, colloiding people have in various contexts. And I think, and I would have to look, but to my knowledge, there isn't really work in that space. Not to my, like I said, we looked very carefully and we didn't find very much. Yeah.
Thanks again.
Thank you all for coming on Friday afternoon. At least you got to sit in AC and not in that vile weather outside.